So here we have problem 32 in section 4.1, and we're interested in seeing whether this solution, this family of solutions, is actually a fundamental solution to the differential equation, second order differential equation given to us. The first thing we notice is this interval here, which is given to us to be from minus pi over 2 to pi over 2, and that's in order that the ln right here be defined, because we need cosine x to be positive. So what we need to do then is to first of all verify that these two functions, cosine x and sine x, form a fundamental set to the homogeneous version of our equation, or of our differential equation. And so that homogeneous version would be y double prime plus y equals 0. And so first we must verify that they actually solve the equation. So if I look at y1 being cosine x, then y1 prime would be minus sine x, and y1 double prime would be minus cosine x. And we can see that y1 double prime plus y1 is actually 0, and so y1 being cosine x satisfies our equation. And you may do the same thing with sine x, and by finding its second derivative you'll see that y plus y double prime would also give you 0, so that sine satisfies the differential equation. So now the next thing we need to do is find out whether sine x and cosine x are linearly independent, and we do that by using the Wronskian. And so we create the Wronskian. We take the first derivative, and right here, to obtain that, when I take the determinant here, I have cosine squared x plus sine squared x. And so that's 1, and that's never 0. And so that tells me then that sine x and cosine x are linearly independent, and they form a fundamental set. And therefore, y equals c1 cosine x plus c2 sine x is the fundamental solution to the homogeneous equation. Okay, now the next thing that we need to see is whether this part right here, which should be the particular solution to this differential equation, actually satisfies the equation. And so for that we'll have to find yp double prime and add it to y and see that we get secant x. So let's do that. So if yp is given by x sine x plus cosine x times the ln of cosine x, then yp prime, and I'll have to use the product rule for both terms. Here I get sine x plus x cosine x, and then I have plus minus sine x times the ln of cosine x plus cosine x times 1 over cosine x times the derivative of cosine, which is minus sine x. So if you notice here, this is cosine x over cosine x, which is 1, and so I have a minus sine of x plus sine x, so I can subtract those, and I'll be left with x cosine x minus sine x times the ln of the cosine of x. Okay, so now we must find yp double prime. And for that, again, I use the product rule, and I have cosine x plus x times minus sine x. And then I have minus, and I'll go ahead and do the product rule now, and I have cosine x times the ln of cosine x plus sine x, and again I have 1 over cosine x times negative sine x, so I have negative sine x over cosine x. Okay, and so now if I go ahead and add yp double prime to y, You see, we have right here this term and this term cancel out when I add those, and so I'll be left with cosine x minus sine squared x over cosine x. And if I use a common denominator of cosine x, oh, in fact, this is plus sign because I need to distribute this minus sign right here, and then I also have this minus sign. And so if I use a common denominator of cosine here, I would have cosine squared x plus sine squared x, and thus 1 over cosine x, or the secant of x. So we can see that yp satisfies the equation. And by definition, then, we now know that y is the fundamental solution of our differential equation.